So, welcome to our week 3 lectures. So, in this week I am going to cover some part of the Levy solution, principle of superpositions, Ridge solution and the basic information that how to use the extended Kantor-Ridge method. Basically all three methods are known as approximate methods. Whereas sometimes we call as exact, that boundary conditions are satisfying exactly, Levy solution, or you say that as well as the Navier solution, both. But in most of the time or in real life, plate is not subjected to only simply supported boundary condition. It may be subjected to clamped, free or a combined all edges. So, for that how to find out a analytical solution. I am putting a stress here that for analytical that approximate methods are preferred, that out of which principle of superposition, Ridge solution or extended Kantor-Ridge method. In these days some new techniques is also discovered or developed like asymptotic method, simplistic approach or some other techniques which are also used to develop the approximate solutions when plate is subjected to some arbitrary boundary condition or loadings. Then another is we may have some numerical solutions. So, there are number of numerical techniques like FDM, finite difference method, BEM, boundary element method, then FEM, finite element method. Then recently DQM, differential quadratron method, very recently developed. So, out of which finite elements over which that some commercial softwares are there. Like Abacus, ANSYS or NISA or some other software. They are based on basically technique is called finite element method. So, there are some advantages, disadvantages. So, in this course I am going to cover only the approximate techniques, but definitely if somebody is interested in developing a numerical solutions, I may provide a small hint or a idea that how to develop specifically FEM solution for a particular problem. Now, in the Levy solution, in the last week we have developed that particular solution, particular part of that. In actual, the solution can be divided into two parts, homogeneous solutions and particular solution. So, based on we have obtained the three special cases, homogeneous solutions, we say that this is a fourth order equation, 4 roots. So, we will say that first case roots are real and distinct and second case same and third case complex conjugate. So, we have developed that what is the kind of the homogeneous function for if our roots are real or distinct, if roots are same or a linear combination of that, or if roots are complex conjugate. Then the particular solution is also derived. So, for that case particular solution can be written as like this, where DMN is nothing but this is. Again we can say that this term is Qn hat in terms of basically a loading kind of thing, load vector. So, I can write a final solution W naught Wn of h which is corresponding to the homogeneous function and Qn is basically load, and along y direction we have chosen, our geometry was that this was x, this was y, and y is equal to 0 and y is equal to b was simply supported. Generally simply supported symbol is by dash dash in some of the book or just putting some s's. So, x is equal to 0 and x is equal to a can have any support conditions. So, now you see the final solution. If I talk about, let us say, first case, my roots are real and distinct. For that case, the homogeneous solution will look like this. If my roots are same or a linear combination, then homogeneous solution will look like this, and if my roots are complex, then my solution homogeneous part will look like this. Now you see here an, bn, cn and dn. These are the arbitrary constant. We have to determine these constant. Then only our solution will be complete. Just writing this W and WH is not going to solve the purpose. So, we have to identify an, bn, cn and dn. Let us say we are going to solve a plate under uniform distributed transverse load with all round simply supported case. We have already a Navier solution for all round simply supported plate. Similarly, we can develop a Levy solution in which we can say that our x axis is also along x a and x is equal to 0 is also simply supported. It may be clamped, it may be free, but I am taking a case where this is simply supported. So, the reason is behind that I am going to tell you that the solution, when you are developing a solution for a Levy type and Navier, what is the difference? First, identify the boundary conditions, whether at x is equal to 0 and x is equal to a. What are the variables need to specify? So, if my plate is simply supported, I am going to say that deflection has to be 0 at x is equal to 0 and x is equal to a. Then the normal moment mxx has to be 0. If another case, if say, let us say this is my clamped, this is my free, so add this as deflection W as well as U and V will also be 0, but we are talking about only a bending case, so deflection as well as the rotation will be 0. Now we see that these are written in a general form W naught and mxx. What is your function of W naught? W naught is Wn of x sin n pi by v. So, basically this is satisfying the boundary condition on y is equal to 0 and b, and this Wn need to satisfy the conditions along x axis. So, when I am saying W naught is 0, it means Wn of x has to be 0. When I am saying moment need to be 0. So, what is the definition of a moment? If you use the plate relations, plate constitutive. So, my mx is nothing but minus of d11 w comma xx minus of d12 w comma yy. This is my moment. Since mx is not our primary variable, so boundary conditions in that form it has to be 0. So, I have written minus dw1. Now, you say it, w naught is capital W1 and sin, so double derivative of that. Similarly, double derivative of y, that has to be 0. So, from here you see that when a two terms like let us say a plus b is equal to 0. So, one condition will be that a independently 0 and b independently 0, or maybe sometimes it may be a combination of kind of things. So, you will say that from this equation it implies that this needs to be, because d11 is a constant, d12 is a constant, this cannot be 0. So, wn comma xx has to be 0. So, now our boundary conditions, w naught has to be 0 and w naught comma xx has to be 0. W naught we know we express like this. So when our roots are real and distinct, so W naught can be written as an of cos hyperbolic lambda 1 of x, bn sin hyperbolic c and so on, plus particular part loading. This is my solution. So what will be my double derivative of W along x-axis? So you will differentiate twice, so lambda 1 square. Similarly, it will common out here, from here lambda 2 square. And Qn is constant if we are saying that it is a uniformly distributed loaded, it is not a function of x. So going to vanish, so W comma x axis 0. Now what is the next step? Substitute x is equal to 0. So when you are going to put deflection, putting x is equal to 0, so sin hyperbolic going to be 0. Here again, so only cos 0, cos hyperbolic 0 will be 1. So an and cn contribution, others will be 0. Similarly, the moment or W comma xx when x is 0, so contribution from there. Then W naught at x is equal to a, put x is equal to a here, so it reduces to like this, lambda a, lambda 2, lambda b, and it's the constant. Similarly from W comma double derivative x, so you can put it lambda 1 square 2 square. So you see it is reduced to a beautiful 4 by 4 matrix, where this is a constant matrix, a n, b n, c n, d n are the constants, and this is the load vectors. So if you know that, if you write a program, then you come to know that these are all the numbers, and then if you invert this matrix, let us say my matrix, I would like to say K final, KB, or I would like to say that K boundary, and this A n, B n, D n, and is equal to Q. So A matrix will be KB of inverse, or because for the present case even you can find in terms of a symbolic form, you put A, B, C, D, and in Mathematica you just make the inverse of that, so some of the terms can be written down. So in this way you are able to solve A n, B n, C n, D n. So for each value of n you will have a set of equations. So you are applying to for loop n is equal to 1, A0, A1, B1, C1, D1, when n is equal to 2, A2, B2, C2, D3. So because this is a series solution, so we need number of terms, then we add it together and check whether our solution is converged or not. So some cases we can write directly now, our solution is not. If you change the boundary condition, instead of a simply supported, you are putting some clamped here and clamped here. So you are going to say at x is equal to 0, my W naught is 0 and W naught comma x is 0. Similarly, x is equal to a. So for that you will have some different kind of constant and you can evaluate. So in this way you have learnt that how to apply a or how to develop a Levy solution for a plate. For any boundary conditions one can develop, so one need to know this matrix. And the next, which is I would like to say is a very important or a specific problem which is covered in every book of theory of plates, whether it is a book of Professor Bhaskara or Professor Chandrasekhara or Professor J. N. Reddy. You take any book, you will find that this standard problem is solved. Before going to there, I would like to come back that Levy solution converge faster than Navier solution. It's one can verify anytime, and it is beautifully given in a K. Chandrasekhara book, that how many terms. Go see. That you require only 10 terms. When you go for a Navier solution, you may require 21 terms or more than that. So I am talking about that plate under uniformly distributed edge moments with all round simply supported. So instead of QZ, now plate is having this kind of moments. QZ is 0, but it is applied, some moment is here. Let us say this is simply supported. Now can you solve that? You see that these two opposite edges are simply supported. Other two edges can have any boundary conditions. So Levy type approach, we can go for that. So only difference where it comes. So you set up a boundary condition at x is equal to 0 and x is equal to a. Deflection is 0, but you have a applied moment at x is equal to 0. Let us say m hat 0. Whenever we say that applied traction, we denote by a hat or some distinct with that the resisting moment. Then x is equal to a m1 hat. So these are the function of y. So like you QZ you have expressed in a single sign series for a Levy case, similarly you will express m0 hat and m1 hat like this, where n bar is nothing but n pi by b. Then what are these? m0 hat and m1 hat, like qn, same 2 by b, 0 to b, and integration over that. So when we are saying this boundary condition, instead of putting moment 0, we are putting the applied value, and QZ is 0. Now anybody can solve this problem and find out this AN, BN, CN and DN. So this solution is very important solution. It helps us basically to develop or applying a principle of superpositions where we need some clamped edges, where we need or the moment will build up. So for that kind of solution we require such analysis. Further, I would like to say that Levy solution, in the present context I have taken y is equal to 0 and y is equal to b simply supported. Similarly, one can choose x is equal to 0 and x is equal to a simply supported, they may have any boundary condition y is equal to 0. So you can switch over. It is not that only always that y0 has to be simply supported, y is equal to b has to be simply supported. It may be other two edges x0 or xa. The main condition is that two opposite edges, either this or this, need to simply supported. So that reverse of that will also be useful for developing a solution for arbitrary support conditions. I think with this basic background, now you can develop a solution or write your own code in a MATLAB or Mathematica and find out the deflections and moments for a plate. That I am talking about a method of superposition. This is a very, I would like to say that powerful method. Let us say we are interested to find out a all round or some say like this, clamped and SS. Can we solve with the help of Navier? No. Can we solve with the help of Levy? No. Definitely we can solve with the help of principle of superposition. So you have to know that where we apply a principle of superposition. The very first that it is the linear solution of a rectangular plate. Whenever your deformation is small and governed by the linear equation, then only you can use the principle of superpositions. The concept behind that, let us say any function under some x is going and some other function, let us say f2 on the same x is going some linearly. So, what will be the result of f1 plus f2? So, if we add those things over that region, proportionality at every point, it gives you the same result. Let us say any function f3, you call it f3. So, we can solve plates with multiple loads. It is very, very important. Let us say our plate is having mechanical loading Qz. Already thermal loading I had explained, some temperature also there, mxt, plus maybe some edge movements, or maybe some concentrated load only, not UDL, or maybe some different kind of loading. So, we will do that. The same geometry, let us say under only Qz plus same geometry under MT plus same geometry under some edge moment. If we add it together, it will give you, so this plate analysis. So, how can you I have done like in structural engineering, in civil engineering, suppose a building is subjected to the wind load, dead load, live load and some other kind of loading, then how do you analyze? So, we will say that, let us say building is under only live load, building is under only dead load or under only wind load, and then you add the solutions. That whatever the solutions you will get, you can add it simply. If you are talking about a plate, if you are, but reason is that that should follow, that deformation should not be large. I mean, it should not be under the non-linear range, it should be under the linear range, then only you can add the solutions. Next, plates with different boundary condition, as I have told you that a plate can we divide such that using Navier and Levy solutions we will get a solution of a plate this kind. So, I am going to explain that deflections, bending moments and stresses in a plate with the specific boundary condition subject to different kind of loading can be obtained by simply adding the solution of plates with the same boundary conditions, but subjected to one kind of a load at a time. That I have said that you just apply Qz, then you applied some hydrostatic pressure, or then later on wind load, then thermal load, whatever. In the next, any distributed moment further, for the example is that a plate is subjected to that having all edges simply supported and subjected to hydrostatic load as well as distributed bending moments along the edges. So, let us say my plate is such that all simply supported, but x is equal to 0, it may have some bending moment plus some hydrostatic load which is a function of x. So, I can analyze that I will just apply under Qx, then under M naught which I have just recently explained in the slide. So, can be obtained simply adding the deflection due to the hydrostatic load plus due to the distribution of edge. So, you got the deflection due to Qz, got the deflection due to the edge moment and add it together at any point you whatever want. So, a plate like clamped here. So, how do you solve that? Let us say divided into two parts. So, this is basically a Navier solution all round simply supported, and this is the plate all round simply supported, but having some moment, built up moment mx and my. So, we can divide it into two parts and we can solve it. So, I would like to refer a journal paper in 2006. Professor Bhaskara with Umasri presented a analytical solution for a flexure of clamped rectangular cross ply plate using an accurate jig type higher order theories. You see that a plate all round clamped as is, So solved by two Levy solutions basically. You take two similarly supported and clamped edges, so there will be applied moment. Similarly, you will take moment on these edges. So this is the superimposed load conditions where they have three load cases. One, applied transverse load, then second, undetermined moments My, Hy, because they have used the higher order theory. So instead of only My, they may have some higher order moments Hy and Jy along y is equal to b and along x is equal to 0 and a. So one can go through this paper. So this is very, I would like to say that beautiful example of a superposition method. So it's a very beautiful research article. One can go through and understand the basics behind that. Now comes to the Ridge solution. I would like to say that Ridge solution is one of the very famous technique used to develop the solutions. So Ridge method is very simple. Any technique which is easy to apply, definitely the undergraduate students, postgraduate students or the programming of that will be easy. So and convenient method of determining the solutions to the plate problems. So basically this technique uses the weak form of the problem, like in the form of minimum potential energy form. In this method, functions are chosen a priori in the form of a series. So we choose a series like that, and where these are the known functions. Which satisfies the kinematic or essential boundary conditions. Kinematic or essential boundary conditions means displacements and rotations. These functions need not to satisfy the natural boundary conditions. Suppose you have a free edge, there you have a boundary condition in terms of forces. So you need not to satisfy that function, will satisfy that force boundary condition. It will satisfy only displacement based boundary conditions. I would like to say that major limitation or disadvantage that its accuracy and convergence depends on the choice of deflection function. For simple cases, one can find out a function which satisfies the boundary conditions. For a difficult one, suppose you don't know the exact function which is going to satisfy the at least displacement boundary condition, you are not able to make that function, then this you will not get a converged solution, or accuracy will be very weak. So how to proceed for such kind of solutions? That you must know the weak form of the equation. So most of the time in the books you will find write out a minimum potential energy and some other kind of things, but recently we have developed del Wi, del We. What are these? Basically change in variation in the potential energy. So we can use those directly, this equation. No need to cramming like what will be my weak form if I want to apply a Ridge solution or a Galerkin or a finite element solution. Basically in all these solutions we are going to use this form. Previously for Navier and Levy solution I have used the strong form of the solution, ordinary differential equation. But since when you are applying for a Ridge solution or a finite element, you have to come up to here using the same, whether suppose you are interested to develop a Ridge solution for a functionally graded plate or a piezoelectric plate or some different kind of a material, then at least you have to come up to here. Know that strains, these things. And then in the next step, instead of developing a governing equation in partial differential form, we are going to use this and using the plate constitutive relations and displacement forms, directly substituting those things. So if generally in the some of the books it is just solved for plate underbending, so only one plate underbending, all three terms will contribute. These are the stretching terms, not contribute. But if you are interested to develop a Ridge solution for a complete, whether stretching as well as bending, then you have to consider this, and this is the loading one, you see. So first of all, substitute the value of del epsilon xx, del epsilon yy, gamma epsilon y. What is that? Del w comma xx, del w comma yy, del w comma xy, and this del w naught. The next step, substitute the value of d11 mx minus d11 of w comma xx plus d12 of w comma yy. Similarly, mxy d12 w comma xx plus d22 w comma xy, and mxy twice of d66 w comma xy, and this thing. Then you can write minus minus become plus. So basically d11 w comma xx del w comma xx plus d12 w comma yy del w comma xx plus w comma xx del w comma yy plus d22 w comma yy del w comma yy, and this contribution and this contribution. So this is the form which we required when we are interested to apply ridge solution. So sometimes students get confused that whether this, how to come up this solution. You just go to our internal work done and external work done principle, develop these things and substitute this mx, my in terms using the plate constitutive relations. So next step is that you assume a solution W naught in this form, and or you can write in a convenient form like this. If you substitute this W naught into this equation, this leads to give a algebraic equation where R can be determined like this. Phi j is a function of xy and C are the unknown constant C1, C2, C3 and F is the load vector. So here you are solving a algebraic equation. So C can be R inverse of F, or sometimes using some Gauss elimination technique or some techniques one can find out this C. Sometimes finding out the inverse may be difficult or it may be ill-treated. So for that point of view, one can use another that linear algebra or linear, I would like to say that matrix techniques solving. Now I am talking about a old method but not widely taught, or it is not really given in most of the books, but it is very elegant method or strong method. So I am going to tell you slight history, that arbitrary support conditions. If we are interested in developing analytical solutions, there may be some exact or approximate, but as you see that for arbitrary support conditions, even the Levy have some limitation, only 2 as is supported, other 2 has to be any boundary condition. So we go for a approximate techniques. Then there may be some numerical techniques, already I have discovered finite element, boundary element, differential quadrature, finite difference, etc. Then semi-analytical techniques are also developed recently. What are these? Basically these are the combination of analytical plus numerical. Basically when we are talking about a 3-dimensional solutions, 3D solutions, the partial differential equation will in x, y and z. So for that cases we solve generally along z direction analytically and x and y using the finite element. So that technique is known as SSFE, state space finite element, or sometimes SSDQM. So recently some of the researchers are using these techniques. So now come about the approximate methods. So there may be Ridge or Galerkin methods. So I would like to say in 1939, so basically the name of Krylov-Kantorovich developed a solution to eliminate the dependency. But since that solution was in Russian language, so in 1958 that book was published in English. So later on that it was known to that there is a solution which is better than the Ridge or Galerkin method. So I am going to explain, and that Krylov-Kantorovich got a Nobel Prize in Economics in 1975 using the linear programming in economics field. Basically Leonard Kantorovich. So Kantorovich and Krylov in 1958, this is the English edition of the book. You see that a general function, any deflection function, if you use a Ridge or Galerkin method, a function is assumed like that Fn is constant and Gn or phi n is a function of x and y, but this function is known function, priori knowns. That satisfy the essential boundary condition for the Ridge case and natural boundary conditions for the Galerkin case. So to I would like to say that eliminate this dependence, because their solution accuracy depends on the initial choice. So Kantorovich proposed in that book, they proposed a method. Let us say you divide a deflection into two bivariate function. Fn is a function of x only and Gn is a function of y only. Then you will get a exact solution along x direction. So in that they have used that one iteration. Let us assume a solution along y, like in Lewis solution along y, okay, and then solve for x. So its accuracy is high. The reason is that because they are solving an ordinary differential equation. They use a weak form and finally we will get an ordinary differential equation. We are going to solve that. So it's more accurate than the Ridge and Galerkin solution. So in this way we get a exact solution along x direction, but it depends upon the initial guess for the y direction. So right now you can say that like Levy type, you are assuming a simply supported some one axis, opposite two axis, and assuming in a Fourier series and solving exactly along x direction. So, but in 1968, Kerr extended this technique. So after that this method is known as extended Kantorovich method, and in which once you solve this, now you say you know this, I am going to solve gy in a iterative fashion. First you assume a gy, solve for Fn, then you take this Fn as a known function and solve Gn. So in this way iterative process is repeated until the convergence is desired. So what are the, I would like to say two basic things, that initial functions need not to require any boundary conditions. Even in Kerr, in original papers in 1968, he has proved with the examples, if you take just a constant or any function, it will satisfy just in 2-3 iterations boundary conditions exactly, and solutions are more accurate and very fast convergence. So after 1968 onward, this method has been applied to study various kind of plates, shells under different boundary conditions and loading, as well as I would like to say that static, dynamic, buckling, transient, and recently we have further, I would like to say that extend to the 3-dimensional case in our recent paper, if you see that. So this I have explained. You choose priori and unknown, and then you take it, then you solve it. So in this paper, in our paper, we have applied this EKM and solved a 2-dimensional problem piezoelectric plate using the extended counterweight method. So, in this, if somebody is interested, they can go for that, or you just extended counterweight method, around 200 or papers are there, some recent review article is also there, one can go through. This is the very good technique one can apply to analyze a problem with arbitrary support condition, and it need to be further, I would like to say, assessed or developed. So, let us say for different kind of geometry or different kind of loading, so that we come to know that whether this technique gives for each and every case accurate and fast converged solutions.